All right, today we're jumping into a research paper with a title that really grabs you. It's wonderfully provocative. More agents is all you need.
So let's get right into it. For the longest time, the big story in AI has all been about scale. The thinking has been, if you want more powerful AI, you just have to build bigger and bigger models. But this paper, it asks a really important question. Is that the only way forward? And believe me, it is a race. We're seeing companies pour billions of dollars into creating these gigantic AI models, with hundreds of billions, even trillions of parameters. I mean, you see it with GPT-4, the Llama family. The whole game has been about building one single super powerful digital brain.
But here's the thing. As good as these models are, they can still hit a wall, especially when you throw really complex problems at them. We're talking advanced math, tricky logic puzzles, or generating complex code. Even the giants can get it wrong. And that is the exact problem that the researchers here wanted to solve.
So, if one single super genius model isn't the complete answer, then what is? Well, the paper proposes a beautifully simple and honestly a kind of counterintuitive idea. They call it the wisdom of the crowd.
Let's just reframe the whole problem for a second. Instead of trying to build one perfect, flawless AI genius, what if you just took a pretty good but, not perfect AI and just asked it the same question over and over again? What if you created a whole forest of individual thinkers and then just let them vote on the best answer?
And that, right there, is the core idea behind what the authors call an agent forest. It's not some new complicated model. It's a different method. You just sample a bunch of answers from the same model and then have them all vote to find the most consistent one. And for anyone who's into machine learning, yeah, that name is a clever little nod to the classic random forest algorithm. It's basically that same logic, but for LLMs.
Okay, so how does this actually work? Let's get into the mechanics, because I know a lot of you wanted to really understand the method, and thankfully, the paper gives us some great visuals to walk through.
So it all starts with one single question or prompt, but instead of feeding it to the LLM agent just once, you feed it in many, many times. By tweaking a setting called temperature, which just controls how creative or random the output is, you can get a whole bunch of different answers to the exact same question. And boom! That's how you create your forest of possible solutions.
So it boils down to this really clean three-step process, which they lay out right in the paper. First, you sample. You ask the model your question, let's say 40 times, and you get this big, diverse pool of answers. Second, you vote. The system then takes all those answers and compares every single one to every other one to see which idea shows up most often. And finally, you select. The answer that gets the most votes, the one that's most popular in the group, is chosen as the final answer. That's it. It's just incredibly simple and elegant.
Okay, the method is simple. I think we've established that. But does this kind of brute force trick actually work? Well, the researchers put it to the test. And the results? They're pretty eye-opening. I mean, that's the multi-million-dollar question, isn't it? After all this talk about building more complex systems, could something as basic as just ask it again and take a vote really move the needle? The answer from the paper is a huge, resounding yes. Just look at these charts from the paper. They show the whole thing in action. Along the bottom, you have the number of agents in the forest, and going up the side, you have the model's accuracy. And look at that trend. It's so consistent across all these different tasks, math problems, coding, even chess puzzles. The more agents you add, the higher the accuracy climbs. Now, this is the result that really makes you question that whole bigger is always better idea. On the left, you've got the huge Llama 2 70 billion parameter model, getting about 54% on a tough math benchmark. But on the right, you have its little brother, the 13 billion parameter model. Using the agent forest method, it scores 59%. Just let that sink in for a second. The smaller model beat the much, much larger one just by using this voting trick.
And the authors say it perfectly themselves. They found that, and this is their term, a brute force ensemble can actually match or even beat bigger, more expensive models. It really suggests that how you use a model can be just as important as its size.
So we know this thing works, but the researchers also dug into when it works best, which is just as important.
It turns out this isn't some universal magic trick, and the details here tell us a lot about how to actually use it.
Check out this table from the paper. It tells a really fascinating story. For a weaker model, like that Llama 2 13B, when you put it on a really hard math task, its performance jumps by a wild 200%. Now compare that to a stronger model like GPT 3.5. The gain is still good, 34%, but it's not as dramatic. And that tells you something really crucial. This agent forest method is like a supercharger, and it works best for less powerful models when they're facing really hard problems.
And they didn't stop there. They also tested an even more powerful version they call Stepwise Agent Forest. The idea is pretty simple. For a problem that has multiple steps, instead of just having one big vote on the final answer, you make the agents vote on the best way forward at each individual step. And as you can see from the charts, this step-by-step voting gives you an even bigger boost in accuracy. It's like you're course-correcting all along the way.
But of course, there's no free lunch here. And the paper is very upfront about the big trade-off. If you use 40 agents, you're running the model 40 times. That means 40 times the compute, 40 times the processing time, 40 times the cost. So you are very explicitly trading more money and power for better performance.
But let's wrap up on the paper's powerful final thought. Because despite that cost, the main takeaway here is just revolutionary in its simplicity. You can get a huge performance boost without having to design all these complicated prompts or frameworks. Sometimes, all you really need is more agents.
And that's really the big question this paper leaves us with. Is the future of AI all about building one single, giant, all-knowing brain? Or is it maybe about creating a whole forest of smaller, collaborative thinkers? It's a fascinating question, and this research proves the debate is far from over. Thanks for joining this explainer.